So moving from Chapter 4 into Chapter 5, both units are trig, but I believe that Chapter 5 is a much easier trig than Chapter 4 was. 4 is really your building blocks and your basics, your basic understanding, your special angles, knowing your trig functions. But Chapter 5, we're just going to go back to and review our law of sines and law of cosines, our area formulas, the area formula in terms of trig anyway. We're going to be introduced to Heron's formula. Now you guys are kind of familiar with Heron's formula because we've done it in a or a calculator program already. But we'll see that formula as well. And then our basic identities and the extension of the identities. And that's where Chapter 5 starts, is with our identities. So I need to review with you first of all then the concept of an identity. There's two types of equations we have in mathematics. There's conditional equations. Those are what we're most familiar with. Conditional equations are only true for a certain selection of your variable. 2x plus 3 is only equal to 7 if x is 2. That's what we call a conditional equation. Versus 2x is equal to x plus x. Is that always true? Is 2x always going to be equal to x plus x? Yes, because x plus x is what? 2x. So 2x is always equal to 2x no matter what I plug in for the variable. That is called an identity. So identities are equations that are always true no matter what you plug in for the variable. And that's what Chapter 5 starts out with. We're going to go through our fundamental identities, the most basic ones. I'm hoping today that we get through the reciprocal identities, the quotient identities, and the Pythagorean identities. If we get farther than that, I'll be happy. But the Pythagorean identities, if you remember from last year, do you remember how many total Pythagorean identities there were? 9. There were 9 total Pythagorean identities, but they were all hinged off of the one Pythagorean identity, and then it was all just doing algebraic manipulation to get the other ones. Okay? So if we get through those today, I'll be happy. And again, we're going about 20 minutes here, and then I'll get you onto your test to finish those ones up. Okay? From the quick review, numbers 1 and 2 here are dealing with what? Inverse sine and cosine. So read this to me. What does this say right here? Yeah, arc sine or inverse sine of 4/5, but what does that mean? We're trying to find an angle whose sine is 4/5, right? Okay, we're trying to find an angle whose sine is 4/5. So 4/5, is that one of our special values for sine? No, it's not. So how would we evaluate arc sine 4/5 or arc cosine 12/13? We would use our calculator. We'd go second sine 4/5, depending on if we were degrees or radians, whichever one we wanted, we'd be able to find that angle whose sine is 4/5 or that angle whose cosine is negative 12/13. 3 and 4, factoring any, I'm hoping we can factor quite easily at this point in our mathematics career. Any questions on how you would factor these two? You know, they're both trinomials. Always look for what first? GCF, then dots, then general trinomial. Always ask, can I factor further? If there's 4 terms, that's a clue into doing what? Factor by grouping, so on and so forth. Simplifying expression, I can't subtract these unless we have a what? Common denominator. What would that common denominator be? XY. So what would 2y really become? 2x over xy minus 3y over xy, giving us ultimately, good, 2x minus 3y over xy. We keep that common denominator as we go through. So any questions on that quick review at all? Okay, so we already recall these basic identities from Algebra 2, and we've already been using them. The basic identities, bless you, are the reciprocal identities. What's the reciprocal of sine? Cosecant. What's the reciprocal of cosine? Secant. What's the reciprocal of tangent? Cotangent. Also lumped into the category of the basic identities are the quotient identities. Quotient meaning what operation? Division. So tangent is the quotient of what and what? Sine over cosine. So tangent is really sine over cosine. So therefore cotangent is cosine over sine. Those are our basic trig identities. And then we'll get into the Pythagoreans. We'll discuss the cofunction identities. Co-functions What is the co-function of sine? Cosine. Tangent? Cotangent. Secant? Cosecant. Now, do you remember the angle relationships, though, with co-functions? Started with the same two letters. Co-functions dealt with what kind of angles? Complementary angles. So the sine of a 30 was equal to the cosine of a 60. Sine and cosine, complementary angles. Okay, so that one dealt with complementary angles. Even odd identities, these are going to be new to us. Okay? We haven't discussed the even odd identities, but we know all of our trig functions are either even or odd. The only two even ones are cosine and secant. And what does even mean? Symmetric about the y-axis. So cosine and secant are symmetric about that. They're even functions. The other four are all odd functions. Well, what does that mean for us? We'll talk about those even odd identities when we get to those. And then being able to prove identities, simplify expressions, and solve some basic trig equations here. So, questions on these ones at all, folks? No. We try to turn everything back into what and what? Sine and cosine. And these all allow me to do this. I'm not going to really deal with cosecant theta. We're going to turn it back into 1 over sine theta. Secant theta is 1 over cosine theta. Cotangent theta is? Are we really going to use that one most often, though? What are we really going to use for cotangent? Cosine over sine. Why don't we want to use 1 over tangent? Well, there's some places that tangent's undefined, right? Is there anywhere where cosine or sine are undefined, though? No, not at all. And then the other ones, you would rarely ever do this, but sine is 1 over cosecant. Cosine is 1 over secant. Tangent is 1 over cotangent as well. We would, rarely ever do this, though, because we want to turn cosecants, secants, cotangents, and tangents back into sines and cosines. Okay? The quotient identities, any question on the quotient identities? Okay. Comfortable with everything that's up here? Question on anything that's up here? Good with those? Okay, so going from the reciprocal and quotient identities into the Pythagorean identities. Now, where does the Pythagorean identity come from? Well, the Pythagorean identities come from, I'm going to bring you back to the unit circle. And I'm just going to look at this first part of the unit circle here. Well, why are we talking about circles when trig is all about what? Triangles. Very specifically, what triangle? Okay, so here we've got a unit circle, and I'm going to make some angle theta. So I've rotated the positive x-axis up theta degrees or theta radians, and now it's up here. And we're dealing with a unit circle, so I know my radius is what? 1. So the distance from here to here is 1. The distance from here to here is 1. Any radii on there is 1. And this is some point P up here. And I know that this is the point XY because I have to go over X units and then up Y units. So that up there is the point XY. Okay, the rectangular coordinate XY. Okay. Well, how are we getting these Pythagorean identities then? Well, the Pythagorean identities obviously come from the what? Pythagorean theorem, which tells me what? Say it in words. Don't tell me what the formula is. I want you to say it in words to me. What does the Pythagorean theorem tell you? The sum of, not sides, because sides could be any three of them. The sum of the square of the legs of a right triangle is equal to the square of the hypotenuse. So the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. We know it better as a squared plus b squared equals c squared, or leg squared plus leg squared equals hypotenuse squared. Well, what are the two legs of this triangle up here? The legs are x, so we could say that x squared plus y squared has got to be equal to 1 squared, which is 1. So x squared plus y squared equals 1 squared. Okay? Well, where are we getting the Pythagorean identity out of this? We're in a unit circle, right? Okay. So in a unit circle, could you tell me what the sine of this angle is equal to? So here's my opposite side, here's my adjacent side, and here's my hypotenuse. Could you tell me, please, what the sine of theta is equal to? y over 1, or just simply y, right? Could you tell me, please, what the cosine of this angle theta would be equal to? X over 1, or just simply x, right? And we really didn't even need to go back to baby trig. I did, with the understanding that maybe we forgot this. But, folks, if we are in a unit circle, what does the x-coordinate represent? The cosine of the angle. What does the y value represent? The sine of the angle. How did we remember that? Well, alphabetically, x comes before y. Alphabetically, cosine comes before sine, right? So cosine is the x-coordinate, sine is the y-coordinate. If we are in a what? Unit circle. If we're in a unit circle. If we're in any other circle, then sine would be y divided by whatever your radius is. X divided by whatever your radius is. But in a unit circle, that radius is 1. So the sine of your angle is just the y-coordinate, the cosine is your x-coordinate. Well, that allows me to make some substitutions then, right? X is what? Cosine theta. So what can I replace x with? We can replace it with cosine theta. And we would then have to square it. Plus, I can replace y with sine theta. Having to square it. And that is now equal to what? 1. Okay, well, we have a mathematics shorthand for squaring sine theta and cosine theta. What do we call it when we square cosine theta? We call it cosine squared theta. But, folks, you've got to make sure that you understand the notation here. Are we squaring the angle, or are we squaring the function value? The function value, right? We're not squaring the angle. We're squaring the function value. We're going to take the cosine of theta and square it. Okay? And, folks, this is an identity. No matter what my angle is for theta, if I square the sine of that angle and add it to the square of the cosine of that angle, it's always going to be what? It's always going to be 1. So this here is the Pythagorean identity. That is the Pythagorean identity. That is where we get all the other 9 from. Okay? So this one has 2 alternate variations, and these 2 alternate variations are just found by solving for different things. Right now we're solved for 1. 1 is equal to cosine squared plus sine squared. Well, suppose I wanted to solve this, though, for cosine squared. What is cosine squared theta going to be equal to? 1 minus sine squared theta. Well, what is sine squared theta equal to? 1 minus cosine squared theta, right? Okay, and now there's 2 alternate variations of this as well. Now, how did we get the alternate variations of the Pythagorean identity? Not reciprocals, no. No, we just simply divide. But I'm going to divide everything by what? First. What's the first term of the Pythagorean identity? Well, if I divide everything by cosine squared, what am I going to get? Cosine squared divided by cosine squared is 1. Sine squared divided by cosine squared is tangent squared. Equals 1 divided by cosine squared is secant squared. Well, instead of dividing everything by cosine squared, I could divide everything by sine squared. Sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared. 1 divided by sine squared is cosecant squared. So I get my 2 other variations by dividing everything by cosine squared, then dividing everything by sine squared. And now, are there 2 other variations for each of these as well? Yes. Okay. Right now I could have that 1 is equal to secant squared minus tangent squared, or that tangent squared is equal to secant squared minus 1. 1 is equal to cosecant squared minus cotangent squared, or cotangent squared is equal to cosecant squared minus 1. How many Pythagorean identities do we have right there then? 9. Now, How do we recognize and spot possible Pythagorean identities? Trig functions need to be squared, and the only numeric value that we could have is 1. So if we see trig function squared plus or minus other trig functions squared, possible Pythagorean identity. If we see trig function squared plus or minus 1, possible Pythagorean identity. Am I asking you to memorize 9 identities? No, you have to memorize the 1. Okay, and then from the 1, you should be able to go on side work somewhere and say, okay, is this 1? Well, let's see. Okay, now I ultimately memorized 3. I memorized the 3 variations. Now, how do I memorize the 3 variations? Well, I know the first one like the back of my hand. You need to know the Pythagorean identity. How do I get the other 2 then? Well, the 2 other C's go together, and then S and T go together. So 1 plus tangent squared is secant squared. 1 plus cotangent squared is cosecant squared. Okay, so the C's go together, the S and T go together, and obviously sine and cosine go together. So sine squared plus cosine squared equals 1. 1 plus tangent squared is secant squared. 1 plus cotangent squared is cosecant squared. And then I've got my alternate variations of them. Okay? Questions on that? Okay, again, make sure you know the 1. Knowing the 3 is nice, but definitely knowing the 1. Okay? So, this example, and then we're going to be back to the test. So find sine theta and cosine theta if tangent theta equals 3 and cosine theta equals or is less than 0. We've done this. We've already done this. We did this in the previous chapter. If tangent theta is equal to 3, well, we think of tangent as being a ratio of sides of a triangle, right? What over what? O over A. So my O is, my A is 1. So what we did is we drew a reference triangle. And we made the opposite 3 and the adjacent 1. We found the hypotenuse by doing what? Pythagorean theorem, right? Okay. And then we knew the 3 sides of the triangle, so sine was the O over H and cosine was the A over H. Okay. So we've already done this example, but now they want us to use identities to do this. They want us to use identities to do this. Okay? Well, let's take a look at this. I know a Pythagorean identity that says that 1 plus tangent squared theta is equal to what? Secant squared theta, right? So I've got 1 plus, what do I know that tangent theta is equal to? No. What do I know tangent theta is equal to, folks? 3. Well, I just need to do what with it? I need to square it. And that's equal to secant squared theta. Well, what is 1 plus 3 squared? 10, right? So secant squared theta is equal to 10. So if secant squared theta is equal to 10, then what is secant theta equal to? Careful, when we take the square root, what do we have to do? Positive or negative radical 10, right? Well, how am I going to determine if it's positive or negative? Well, that's why they told me this piece of information right here. Where is tangent positive? 1 and 3, right? Where is cosine negative? 1 or 3? It's got to be quadrant 3. We're dealing with a quadrant 3 angle. Secant and quadrant 3. What's positive in 3? Tangent and cotangent. Secant has to be, secant's got to be negative. All right, folks, if secant is negative radical 10 over, then what does cosine theta have to be? Negative 1 over radical 10, right? No, you don't need to rationalize it now. That was important in Algebra 2 because rationalizing was an important concept for Algebra 2, but if you were in trig, a specific trig course, you would leave that like that. Okay? Could I do the same thing to find sine? Yep. Actually, I'm going to use this now. I know that tangent theta is equal to what over what? Sine theta over cosine theta. Do I know what tangent theta is equal to? 3. Do I know what sine theta is? No, we're trying to find that, right? But do we know what cosine theta is? Negative 1 over radical 10, right? So can I undo that to find sine? Yep. How do we undo division? Multiplication, right? So sine theta is going to be equal to 3 times negative 1 over radical 10. So what is sine theta going to be equal to? Careful. Negative 3 over radical 10. Which way do I do these? Do I do them with reference triangles or do I do them with identities? I always do them with reference triangles. Why? Because that's what trig is all about, is triangles. I always go back to the right triangle if I know a trig ratio to go to those. But can we solve them with identities? Absolutely we can solve them with identities. Are we expected to solve them with identities in this chapter? Yes, we will be solving them with identities in this chapter. Okay? And there's a multitude of identities I could have gone back to. Okay, I would recommend that you start looking at the 5.1 homework assignment. Get a start on it at least. And we'll pick this up tomorrow. Questions? All right.